All right, folks, it is Tuesday morning. I think it is almost April. It's March 31st, and I'd like to cover the first two sections of chapter 30 today in these notes. And since we're so disconnected, I would love to get some feedback from you, the few of you who are following along, as to whether these videos are helpful. I'm basically covering the same material that's in your textbook, but I'm trying to describe it or explain it as I go. So please send me an email. Email, and let me know if this is helpful. If it's not helpful, I will stop doing it. It takes me a fair amount of time. But partly that's because I'm trying to figure out how to record these screens and how to use OneNote. All right, so here we go. We have already talked about chapter 29, and I want to tell you first how chapter 30 is different from chapter 29. And so in chapter 29, we were interested in quantifying the force that was felt by a moving charge in a pre-existing magnetic field. And so we did something like the force is equal to the size of the charge times how fast the charge is going crossed with the magnetic field. So that's what we did in chapter 29. Really, it's about the force that's felt by a charge that's moving in a pre-existing magnetic field. So this magnetic field, who knows where it comes from? Who cares? We were just thinking about the force that's felt by a charge. Now in chapter 30, it's all about the magnetic field. Where does this magnetic field come from? Where on earth does it come from? Fields are always a little harder to get a grasp on. Forces are pretty straightforward. We can measure them. Forces are pushes and pulls. So we can feel that push or pull. But fields are all around us, and yet they're invisible. So they're, we can't see them, we can't smell them, we can't taste them, we can't touch them. So how do we know they're there? That's makes it a little bit more difficult. All right. So chapter 30 is really all about where do the magnetic fields come from? So I'm going to go back in history a little bit, even pre-1800s, to talk about magnetism. So back thousands of years ago, I think it was about 2 BC, navigators were using lodestones, because these stones would point towards magnetic north. And now we know that these stones were made of magnetic material. Magnetite is a naturally occurring magnet. Okay, and they would line up with the magnetic field of the Earth, and in doing so would help navigators to figure out the direction of north. And so that was being used, a very long time ago. And so certainly by the mid-1800s, people were starting to get a grasp of the power of magnets. And they were also, after Newton's laws in the 1600s, they were also able to describe them in terms of forces. So when a South Pole came close to a North Pole, they would say that there was a force of attraction. And on the other hand, if a South Pole came close to another South Pole, then they would describe that in terms of the force as a repulsion. So these field lines are sort of pushing away from each other. Ew, get away from me, repulsion. Okay, so attraction and repulsion was something that scientists were familiar with, certainly by the middle of the 1800s. But a couple of scientists at that time, named Biot and Savart, wanted to quantify the magnetic field. They wanted to be able to talk specifically about the size and direction of the magnetic field. And they set up some experiments using a U-shaped magnet, which has both a north and a south pole, that are pretty close to each other. And they put a wire in between those poles. This is just a copper wire. All right. So without any current flowing through it, that copper wire just is not influenced at all by that magnetic field. However, as soon as they turned on the current, that wire jumps. And that's something that you can actually observe in your own house probably. Okay, if you put a strong magnet near a wire that's carrying some current, you're going to see that wire start to jump. It'll move. And that's kind of interesting. So what does that imply? Well, here's the pre-existing magnetic field. There's some magnetic field there that they already knew about. If the wire is affected by that magnetic field, it must be setting up its own magnetic field. In other words, back here, what did we know? We knew that this magnet was affected by this magnet. So what do we have down here? We have this U-shaped magnet, which is affecting another magnet, the magnet that's set up by the current carrying wire. And so the discovery is that current carrying wire, current creates magnetic fields, or moving charges create magnetic field. So they wanted to be able to quantify that. So first they made some observations, and these observations are going to be probably reminding you of the electric field. So the magnetic field they observed is directly proportional to the current. Okay. It's also inversely proportional to the square of the radius. And that looks very familiar from electrostatics. And last but not least, the magnetic field is also proportional to the sine of theta, which makes me think of cross product. Okay, the sine of the angle. What angle? Where theta is measured between ds, the length vector, and the radial vector. So I need to draw a picture to show you what that means. All right. So here is a little length of current carrying wire. It's not perfectly straight. It's got some current flowing in it. Let's say the current's going in here and it's coming out here. And I want to think about the magnetic field at this point P, a little bit above the wire. And the way to do that is to think about the magnetic field that might be set up by a little section of the wire ds. So here's my little ds vector. Actually, that's not a very good vector to use. So let me just get rid of that. Whoops. Whoop. Get rid of that. I'm wondering if you can hear my radio. I don't know what this music is. All right, there's ds, little piece of length. Okay, now I can draw the radial vector a little easier. So from ds over to the point P that I'm interested in, there's my radial vector. And you can see that there's an angle in between those two vectors, ds and r. And that angle is affecting B at the point P. And so B would be the greatest if the angle were exactly at 90 degrees. So we'll see that in a second. All right. And so those are the observations that were made by Biot and Savart and led them to the Biot-Savart law for how to find the magnetic field due to a current, due to moving charge. Okay, B. So B is equal to, and it's going to be a cross product. So it is mu sub 0, fundamental constant in physics, mu sub 0 times I divided by 4 pi times the integral of that little ds crossed with r hat. And that just means the radial vector, the unit vector, 1 unit long, r hat. So it points in the direction of the radial vector, but it's only 1 unit long, divided by r squared. So this is the Biot-Savart law, and we're going to make use of it. Okay, so I'm going to put a big box around it because it's important. Now I need to talk about mu sub 0. Mu sub 0 is called the permeability of free space. Permeability of free space. Similar to the permittivity of free space, E0, Permeability of free space comes up in magnetism, and it's equal to 4 pi times 10 to the negative 7 Tesla meters per amp. Yikes, another fundamental constant. All right, so we're going to talk about two specific examples of the Biot-Savart law. One is specifically how to find the magnetic field that is set up by a current carrying wire. And so here I have a little current carrying wire. Let's assume the current is moving vertically upward in that wire. And I want to be able to find the magnetic field using the Biot-Savart law. All right, so I'm going to work a little bit backwards here. What I'm going to do is give you the answer first, and then we're going to figure out how to find the answer. All right, so what is the magnetic field due to a current carrying wire? Well, let's think about the direction first. So we can use our right-hand rule to find the direction of the magnetic field. If you take your thumb and you point it up in the direction of the current, so your thumb points in the direction of the current, and then you look at your fingers and how they're curling in your hand. So here's my thumb pointing up, and then my fingers sort of curl like this, right? Fat fingers. And there's the rest of my hand. Ooh, I don't know. That's a pretty nasty looking hand, but you know what I mean. This is my thumb. So what does that tell me about the direction of the magnetic field? It circles around this current carrying wire. The magnetic field looks like that. Okay, it circles. And so it's coming out of the page over here and it's going into the page over here in concentric circles. It's probably getting weaker farther away from that wire, and it's stronger very close to that wire. And that's what the magnetic field looks like. The right hand gives us a sense of what the magnetic field does near a current carrying wire. All right. What about the size or the quantity? So the size is mu sub 0 times the current divided by 2 pi times r, how far away my point is from that wire. So if I'm interested in this point P, and this is r from point P to my current carrying wire, the magnetic field is inversely proportional to r at that location. All right, there we go. Now what we need to do is prove it. Prove it using Biot-Savart law. Now, if you were a junior, and you aren't juniors anymore, thankfully, if you were a junior, I would just give this to you, and we would not be thinking about how to prove it, because proving it has to do with a lot of, sorry about all those little notifications popping up. Proving it has to do with making some trigonometric substitutions. And when you are a junior, those might be brand new to you, but now that you're a senior, you've done a lot of trig substitution. So I'm going to assume that you can use some trig substitution here in proving this using Biot and Savart. Okay. So we need to set up a picture first. And so come on, there we go. I've tried to draw for you a little current carrying wire. And what I'm going to do is superimpose an x-axis on that current carrying wire. So there is x. And then perpendicular to that, I'm going to make y. So there's my y-axis. And I'm going to also draw a little ds. There's my little ds vector. And I'm going to put my point of interest here, P. So I'm interested in finding the magnetic field at P rather. Find the magnetic field at point P using Biot-Savart law. That's what I want to do. So I'm going to make my picture pretty clear. Let's just say that the distance between P and the x-axis is A. Let's just say that my radius vector or my radial vector goes from here up to here. There's r. And in fact, what I'm really interested in is little r hat, the unit vector, but that's the direction. And then I also need the angle So here's theta 1. And I would like to find the total magnetic field due to this section of wire that goes from here all the way up to the other side, about right here. So I would like it to be nice and symmetric. That makes the math pretty easy. All right. So I'm going to start to integrate here, and I'm going to integrate all the way up to here, where this is theta 1. My initial angle is theta 1, and here's my theta 2. Again, the angle's measuring with respect to the x-axis. So there's my picture of what I want to do. I want to find B at point P. I want to find B at point P. So we're going to start with the Biot-Savart law, and then we're going to derive it using a couple of trig substitutions. So here we go. B is equal to, according to the Biot-Savart law, mu sub 0 I divided by 4 pi times the integral of dx or ds times the sine of theta. Whoops, let me start with the actual cross product. So ds cross with r hat divided by r squared. That's what I really have, all right? Now let's think about these things. ds is along the x-axis, so I'm going to call it dx. R has a size of 1, right? Its size is 1, so I'm going to substitute in a 1. And I'm going to write this using the magnitude formula, the magnitude of the cross product. But I have to think about the direction of the magnetic field. So let's write this using the sign. Mu sub 0 I divided by 4 pi, integral from theta 1 to theta 2. ds is really dx. R is really 1. I need the sine of theta divided by r squared. So already it's looking a little bit better, but I do need to think about the direction, because when I take away this cross product, I'm taking away information about the direction. So what is the direction using the cross product? And again, if you use your right hand rule and you point your thumb to the right side of the page and look at the way your fingers curl, the magnetic field up here is coming out of the page and it's curling around and pointing into the page here. So it's circling like this. All right, there's the magnetic field out of the page on top. And that's where I'm interested in. My point of interest is at the top of the page. So it's out of the page. All right. Now, just cleaning this up a little bit then, B is equal to mu sub 0 I divided by 4 pi, integral from theta 1 to theta 2 of sine of theta times dx divided by r squared. So I need to relate those variables. Relate sine of theta, x, and r. And I'm going to use trig to do that. That's going to be pretty straightforward because I've got a big old right triangle here, right? Where this vertical distance is a, here is x. And by the way, since this is on the left-hand side, I'm going to make this negative x, and this side is going to be positive x. Okay, negative x, positive x. The vertical distance is a, and my hypotenuse is r. And my theta angle is stuck right in there. So I'm going to use a couple of trig substitutions. Here we go to try to be quick. Sine of theta, opposite over hypotenuse. So sine of theta is a over r. That means that I can write r as a divided by the sine of theta, which is really a times the cosecant of theta. So nobody would have liked that probably in your junior year, but I'm going to go ahead and use it now. Something similar for tangent. Tangent of theta is the opposite side over the adjacent side, negative x. And that gives me a way to write x. X is equal to a divided by tangent, which is really the same as a times the cotangent, a cotangent of theta, and with a negative sign there. All right. Now in my formula, I'm not too worried about x. What I really need is dx. So I need to take the derivative. So dx d theta is what? Negative a. The derivative of cotangent is negative cosecant squared. And so that means dx is equal to a cosecant squared of theta d theta. So I'm going to make these two substitutions, one for r and one for dx in my Biot-Savart law, and simplify. That's all we need to do. So the rest is easy. Rest is cake from theta 1 to theta 2. Sine of theta stays where it is. Dx is a cosecant squared theta d theta. R gets squared. So r is really a cosecant theta, a squared cosecant squared theta. Okay, so you can see that making those two substitutions really simplifies things. Ooh, that goes away. Thank goodness. One of the a's goes away, and we're left with something that is pretty straightforward. B is equal to mu sub 0 I divided by 4 pi times the integral from theta 1 to theta 2 of the sine of theta d theta, which is the same as mu sub 0 I divided by 4 pi times what? Negative cosine theta from theta 1 to theta 2. All right. Now I have to do something that's a little bit tricky here, but I think you're going to like it because it's kind of cool too. So mu sub 0 I divided by 4 pi. This is going to be negative cosine theta 2 minus negative cosine theta 1, which is finally b is equal to mu sub 0 I divided by 4 pi cosine theta 1 minus cosine theta 2. Now here's where the tricky thing comes in. If this is an infinitely long current carrying wire, what happens to the angles? Well, let's go back up here and look. If I think about making this wire infinitely long, way out here, I'm drawing my radial vector to point P, starting way out here. What happened to my angle? It got a little bit smaller. If I go farther out, it gets a little bit smaller still. The farther out I go, the smaller that angle gets. And then what happens to theta 2 over here? The farther out I go, the bigger this angle gets. In fact, this angle here approaches 0, and this angle over here approaches 180 if my wire is infinitely long. Well, 0 and 180 are kind of nice numbers to work with, especially with the cosine. So if theta 1 is 0 and theta 2 is 180, haha. So cosine of 0 is 1 minus, and this is really negative 1, which gives me 2. And so b is equal to mu sub 0 I divided by 4 pi times 2. b is mu sub 0 I divided by 2 pi. And there's an r that I forgot to bring out. There should be an a here. Mu sub 0 I divided by 2 pi a. Where's that a? Some of you already probably realized it's here, and I forgot to bring it out. So there's an a there, there's an a there, and there's an a there. I dropped the a, and I did not mean to do that. So there's an a in this answer. So here is the magnetic field due to a current carrying wire. Cool. All right, that's where it comes from. So pretty easy integration, but you had to make a couple of complicated substitutions first. So I'm going to ask you to please look at your textbook for example 30.3. Another really important application of the law of Biot-Savart is a loop of current carrying wire. Motors and generators all have loops of wire in them. And so if we have a loop of current carrying wire, what is the magnetic field out here at some point P? What is the magnetic field due to that current carrying loop of wire? Please look at example 3030. That's an important result that I won't take the time to prove, but it's definitely something that you're going to use. One thing I will take the time to do is to talk about the force between two parallel wires. So parallel wires exist all over the place. And if you look up at the sky near your house, you might have some telephone poles. Telephone poles have wires that are parallel to each other carrying current. And those wires do affect one another. All right. So I1 and I2. There we go. I1 and I2. All right. So I would like to figure out how these forces or how these wires are either attracted or repelled based on the current that they carry. And so I'm going to look at the force on I1. The force on I1 due to the presence of I2 nearby. That's what I'm interested in doing. So that I2 sets up a magnetic field around itself, right? That looks like this, B. And up here, it is pointing out of the page, and down here, it's pointing into the page. And all you need to do is set up your thumb so that it's pointing in the direction of I2, and your fingers are curling out of the page up here and into the page down here. So wire 2 sets up its own magnetic field. That magnetic field affects the current moving in wire 1. And so that's what we want to do. We want to be able to write down a force, write down the formula for the force that exists on wire 1. So just using your right-hand rule, again, a different way. Remember the force acting on wire 1 due to wire 2 is I L cross B. Okay, so here's the current I. This is a little dl. And if you cross that with the magnetic field, which is out of the page, you should be able to convince yourself that the force is pointing down. So it's an attractive force. Wire 1 is being pulled towards wire 2. So now let's just be careful with our variables. The force on wire 1 due to wire 2 is equal to the current in wire 1 times the length of wire 1 times the magnetic field set up by wire 2. And I know now a way to write down the magnetic field set up by wire 2. There it is. All right. And so the force acting on wire 1 due to wire 2 is I1 times the length of wire 1 times what? And so that was mu sub 0 times I2, the current in wire 2, divided by 2 pi times the distance away, A. And here A would be the distance between these two wires. All right, cleaning that up one more time. F12 is equal to mu sub 0 times I1 times I2 times the length of the wire divided by 2 pi A. That's the total force acting on wire 1. A little more useful is the force per unit length. The force per unit length, mu sub 0 I1 I2 over 2 pi A. This gives me the force that acts on each meter of that wire. All right, pretty cool stuff. Next up is Ampere's law. So that's coming. That is section 33. And so I will post a video for that by the end of the week. But between now and then, if you would try to work 1 through 23 odd. And also don't forget to send me an email and tell me if this is helpful. This format of like making these videos using OneNote, blah, blah, blah. It's a little bit difficult for me to get used to using. You might be able to tell that, but I will get better at it as I do more of it. So I hope that's helpful to you, but please let me know if it is or if it isn't, because that'll help me figure out how to use my time. All right. Have a good day. Bye.